For millennia, humanity has gazed upon the horizon, not merely to admire its beauty, but to discern its end. Why do we, as a species, possess such an unyielding urge to define the boundaries of our existence, to draw maps that inevitably, tantalizingly, point to what lies beyond the known? This impulse stretches far back, reaching into the dusty, sunlit halls of the Library of Alexandria, where, around 150 Anno Domini, the brilliant mind of Claudius Ptolemy meticulously compiled his monumental work, the Geographia. This wasn't just a collection of charts, it was an attempt to catalog the entire known world, a testament to humanity's obsession with mapping its territory. Yet, even in Ptolemy's detailed representations, the maps carried an unspoken truth, often inked with chilling, evocative words. Hic sunt dracones. Here be dragons. These fearsome annotations weren't simply fanciful warnings of mythical beasts. They were a stark acknowledgement of the unknown, an admission that every map, no matter how grand, reached an inevitable edge. This deep-seated psychological need for a defined world, for a cosmos that could be contained and understood, has shaped our collective consciousness for ages. It was the same primal fear of the void that propelled legendary explorers like Ferdinand Magellan. In 1519, when his 5 ships embarked on their perilous circumnavigation of the globe, every sailor understood they were sailing into a vast, uncharted canvas, a realm where known dangers merged seamlessly with unimaginable terrors. Magellan's journey, which concluded in 1522, was not merely a physical voyage. It was a psychological battle against the very concept of an endpoint, a defiance of the dragons lurking just beyond the known shores. Do not think these cosmic anxieties are a relic of a distant, unenlightened past. The profound questions we grapple with today regarding the universe's ultimate limits are not new. They are a direct continuation of this fundamental human impulse to map our territory, an urge that has, time and again, mistaken the limits of our perception for the absolute limits of reality itself. Consider the monumental shift from a flat Earth model to a spherical one. This wasn't an elimination of the concept of an edge at all. Instead, it radically transformed its nature. The physical boundary of a flat world, a cliff over which ships might fall, transmuted into a psychological frontier, the daunting, almost spiritual challenge of circumnavigation. The edge no longer existed as a place you could reach and then stop. It became a horizon, forever receding as you advanced. This historical and psychological framework serves as a profound analogy for our entire cosmic journey. Our relentless quest to understand the universe's edge is, in essence, the ultimate act of cartography. We are perpetually haunted by the same cartographer's ghost that has always pushed us, compelled us, to peer beyond the known world. From the mythical Pillars of Hercules, once believed to mark the gateway to the Atlantic's terrifying expanse in antiquity, to the elusive, ever-expanding edge of the observable universe today, the impulse remains identical. This drive, this insatiable curiosity tempered by an underlying fear, is deeply encoded within our very cognitive biases. It is a product of millennia of evolutionary pressures that favored understanding immediate, finite environments, making the sprawling, boundless, and often overwhelming concept of infinity profoundly counterintuitive and, for many, genuinely frightening. For centuries, humanity's cosmic map was largely confined to our own celestial neighborhood. We believed we lived in a grand, singular island of stars, the Milky Way, encompassing all there was. But then, a quiet revolution began, not in the grand halls of academia, but in a dusty annex, amidst stacks of photographic plates, where the meticulous work of a forgotten astronomer would shatter our perceived reality and unveil a universe unimaginably vast. It was the early 1900s, and at the Harvard College Observatory, a group of women, often referred to as human computers, toiled behind the scenes, their astronomical work frequently dismissed as mere women's work. Among them was Henrietta Swan Leavitt, a diligent and perceptive American astronomer. Her task, seemingly mundane, was to meticulously catalog variable stars, those celestial beacons that rhythmically brighten and dim over time. She focused on a particular type, the Cepheid variables, named for the star Delta Cephei. Leavitt's work was painstaking, examining thousands upon thousands of photographic plates, each one a snapshot of the night sky, capturing the flickering light of these distant suns. What she discovered in 1912, after years of this unglamorous but utterly essential work, was nothing short of miraculous. Leavitt observed a precise, undeniable relationship. The brighter a Cepheid truly was, its intrinsic luminosity, the longer the period of its pulsation. This wasn't just a correlation, it was a cosmic key. If you could measure how quickly a Cepheid pulsed, you could know its absolute brightness, its true power output. And if you knew its absolute brightness and could measure how bright it appeared from Earth, you could calculate its exact distance. It was the first reliable, standard candle in the cosmos, a tool of unimaginable power that astronomers had yearned for centuries. Until Leavitt's quiet breakthrough, there was no dependable way to gauge the true scale of the universe beyond a few nearby stars. Imagine trying to navigate an ocean in total darkness, with no compass, no maps, only glimpses of distant, flickering lights whose true distance remained a mystery. This was astronomy's predicament, and Leavitt offered the first dependable light source. Yet, even with such a profound discovery, the universe's true scale remained fiercely debated. The scientific community was still locked in a profound uncertainty regarding the very nature of those faint, fuzzy patches of light scattered across the night sky, often labeled as nebulae. Were they swirling clouds of gas and dust within our own Milky Way, perhaps nascent solar systems forming? Or were they, as some daringly proposed, entirely separate island universes, galaxies in their own right, millions of light-years away? This question came to a head in 1920 during what became known as the Great Debate at the National Academy of Sciences in Washington, D.C. American astronomers Harlow Shapley and Heber Curtis stood on opposite sides of this cosmic chasm. Shapley argued passionately that the Milky Way was the entirety of the universe, and the nebulae were merely internal phenomena. Curtis, on the other hand, championed the island universe theory, suggesting that many of these nebulae were vast star systems, far beyond the boundaries of our own. The scientific evidence at the time was inconclusive, the arguments complex, and the stakes immense. The debate ended without a clear victor, a testament to the scientific uncertainty that reigned before Leavitt's key was fully utilized. The stage was set for the chapter's astonishing climax. In 1923 and 1924, at the Mount Wilson Observatory in California, perched high above the Pasadena lights, stood Edwin Hubble, armed with the formidable 100-inch Hooker telescope, then the largest and most powerful telescope in the world. Its giant, gleaming mirror, a masterpiece of optical engineering, allowed him to resolve individual stars within the Andromeda Nebula, that prominent fuzzy patch visible to the naked eye. And among those individual stars, Hubble found them, Cepheid variables. He meticulously observed their rhythmic pulsations, just as Henrietta Leavitt had taught. Applying Leavitt's period luminosity relationship, Hubble performed the calculations. The numbers that emerged from his equations were staggering. Andromeda was not a cloud within our galaxy. It was a separate galaxy, a colossal island universe of stars, positioned not hundreds of thousands, but millions of light-years away. To grasp this scale, consider that a light-year, the distance light travels in 1 year, is nearly 6 trillion miles, or 10 trillion kilometers. Andromeda was not merely 1 million light-years away, but over 2 million, a distance so vast that the light we see from it today began its journey before early humans walked the Earth. This wasn't merely another astronomical discovery. It was a profound psychological break, a cataclysmic shift in human perspective. The moment our perceived reality, the Milky Way, was shattered, revealing a cosmos vastly larger, infinitely more populated, and far more complex than anyone had ever dared to imagine. Our cosmic map, once a small, familiar island, exploded into an ocean teeming with uncounted galaxies, each containing billions upon billions of stars. It created a new, far more distant edge to our understanding, a horizon that receded with every new observation. It is crucial to understand that this new, grander map of the universe was not simply found, waiting to be stumbled upon. It was painstakingly built, piece by piece, through generations of human ingenuity, technological innovation, and the quiet, persistent, often unheralded work of brilliant minds like Henrietta Swan Leavitt. Her forgotten genius provided the crucial measurement tool that unlocked the true scale of the cosmos, forever redefining our place within it. For all of humanity's boundless curiosity, for all our maps and our telescopes that push the very limits of vision, there exists a profound and unyielding barrier. It is not a boundary in space, not a physical edge you could ever reach, but a shimmering, incandescent wall at the very beginning of time itself. It is a cosmic threshold beyond which our sight, no matter how advanced, is rendered utterly blind. How could such a thing exist? How could the universe hide its ultimate genesis from us, not behind endless void, but behind a curtain of pure light? The story of this cosmic barrier begins, remarkably, not with grand observatories or theoretical breakthroughs, but with a nagging, persistent problem: pigeons. It was 1965, and at Bell Laboratories in Holmdel, New Jersey, 2 American radio astronomers, Arno Penzias and Robert Wilson, were struggling with a strange, irritating hiss in their powerful horn antenna. This antenna, a massive structure standing 50 feet high, or 15 meters, was designed for satellite communication, yet it picked up a faint, unwavering noise from every direction, day and night. They cleaned out pigeon droppings, assuming the birds were the source of the interference. They meticulously checked every circuit, every wire, even the antenna's internal temperature, which they measured at an excruciatingly cold 4 degrees above absolute zero, or negative 269 degrees Celsius. Nothing worked. The faint uniform hum remained. It was a mystery that baffled them, a cosmic static that wouldn't go away. Unbeknownst to Penzias and Wilson, just 30 miles, or 48 kilometers away at Princeton University, another team of scientists, led by Robert Dicke, was deliberately searching for precisely what the Bell Labs duo had accidentally stumbled upon. Dickey's team, inspired by the theoretical predictions laid out by physicists like George Gamow, Ralph Alpher, and Robert Herman back in the 1940s, knew that if the universe had indeed begun with an immensely hot, dense state, a Big Bang, then there should be a faint afterglow. This afterglow, stretched and cooled over billions of years, should still permeate the cosmos as a uniform, low-energy microwave radiation. They were building their own antenna, specifically designed to detect this ancient light. The profound irony is that Penzias and Wilson had already found it, mistaking the universe's most ancient message for mere pigeon droppings. What Penzias and Wilson had detected, and what Dickey's team was seeking, was the cosmic microwave background, or CMB. It is often referred to as the echo of the Big Bang, but that analogy, while evocative, can be misleading. It is not an echo in the conventional sense, nor is it a wall in the spatial dimension, a barrier we could fly towards and collide with. No, the CMB is a wall in time. It is the surface of last scattering, a frozen snapshot of the universe when it was an impossibly young 380,000 years old. To grasp this, consider the entire age of the universe, currently estimated at 13.8 billion years. 380,000 years is but a blink, a mere fraction of its infancy. Before this pivotal moment, the universe was an inferno. It was filled with a superheated, opaque plasma, a dense, swirling soup of fundamental particles, electrons, protons, and photons, all moving too energetically to form stable atoms. Crucially, in this plasma, light particles, or photons, could not travel freely. Every photon was instantly scattered, absorbed, or bounced off the free electrons and protons, much like trying to walk through an impossibly dense fog. The universe was, in essence, an impenetrable cosmic fog. No light could escape it, and therefore, no light from that era can ever reach our telescopes. Then, something fundamental changed. As the universe expanded, it cooled. Its temperature dropped below 3,000 degrees Celsius, or 5,400 degrees Fahrenheit, cool enough for electrons and protons to finally combine and form the first stable neutral hydrogen and helium atoms. This event, known as recombination, was the moment the cosmic fog cleared. The universe suddenly became transparent to light. The photons, previously trapped, were now free to stream across the cosmos. These are the very photons we detect today as the cosmic microwave background. They have been traveling for over 13 billion years, redshifted and cooled to a mere 2.7 degrees above absolute zero, or negative 270.42 degrees Celsius. Think of it this way. Imagine standing in the middle of an extremely dense fog here on Earth. You can see the fog itself. You can see the light reflecting off the water droplets right in front of your eyes. You can even see a short distance into the fog, perhaps a few yards or meters. But can you see through the fog to what lies beyond it? No. The fog itself is the source of the light reaching your eyes, effectively blinding you to anything past its immediate density. The cosmic microwave background is precisely this kind of fog. We are looking into it, seeing the light from its surface, from the moment the universe became transparent. But we can never see through it, because before that moment, the universe was entirely opaque. This, then, establishes the true boundary of our observable universe, a temporal horizon. It is a fundamental limit to our vision, imposed not by the inadequacy of our telescopes, but by the very laws of physics, by the nature of light and matter in the universe's earliest moments. We can never peer past this glowing wall, back to the ultimate origins of the cosmos, not because the light isn't there, but because it was forever trapped behind the impenetrable veil of a universe too young, too hot, and too dense to reveal its own beginning. Having journeyed to the very edge of our cosmic vision, peering at the glowing wall of light that defines the observable universe, we now confront an even more profound question. It is not what lies beyond this temporal barrier, but what is the very fabric of the universe shaped like? Is the grand stage upon which all cosmic drama unfolds flat, curved, or something else entirely? This isn't a question of destination, but of geometry, of the fundamental form of reality itself. For centuries, mathematicians and philosophers have grappled with the nature of space. In 19th century Germany, the brilliant mathematician Carl Friedrich Gauss, among others, pondered how one might deduce the curvature of a surface without ever leaving it. His elegant solution involved something as simple as a triangle. On a flat, two-dimensional sheet, the angles of any triangle you draw will always add up to exactly 180 degrees. This is the geometry we learned in school, the familiar Euclidean space. But what happens if the surface itself is curved? Consider a vast cosmic sphere, a universe with positive curvature. If you were to draw a giant triangle on the surface of an enormous ball, connecting three distant points, you would find that the sum of its angles would be greater than 180 degrees. The lines would converge, almost as if the space itself were pulling them together. Such a universe would be finite in extent, like the surface of a globe, yet it would be unbounded. You could travel in any direction forever, and eventually return to your starting point, without ever encountering an edge. There would be no center, no border, only a continuous, closed surface. Now, shift your perspective to a universe with negative curvature, often described as saddle-shaped. On such a surface, drawing a triangle would yield a vastly different result. The sum of its angles would be less than 180 degrees. The lines would diverge, spreading out as if repelled by the very geometry of space. This kind of universe would be truly infinite, stretching out forever without end, its vastness expanding boundlessly in all directions. Like a saddle, it would curve away from itself in every dimension, offering an endless, ever-stretching expanse. Finally, there is the possibility of a perfectly flat universe, a vast, cosmic sheet. In this scenario, just like on our everyday flat paper, the angles of any triangle would sum to precisely 180 degrees. Such a universe, too, would be infinite, a boundless expanse of Euclidean space. Einstein's monumental theory of general relativity revealed that the amount of matter and energy within the universe dictates its curvature. If there is enough matter and energy, the universe bends inward, creating positive curvature. If there is too little, it curves outward, resulting in negative curvature. But if the universe possesses precisely the right amount of mass energy, it remains perfectly flat. Measuring this cosmic geometry requires tools of unparalleled precision. Enter the European Space Agency's Planck satellite. From 2009 to 2013, this remarkable spacecraft orbited the Earth, meticulously mapping the cosmic microwave background, that ancient light from the universe's infancy, with unprecedented accuracy. Planck wasn't just taking a picture, it was scrutinizing the tiny temperature fluctuations within that primordial glow. These minuscule variations, only millionths of a degree different from one another, are the seeds of all structure in the universe, the very faint fingerprints of the Big Bang itself. But more importantly for our question, they also act as a cosmic backdrop, like a giant cosmic ruler, allowing scientists to measure the geometry of space-time itself. The way these fluctuations are distributed, their size and their patterns, are incredibly sensitive to the overall curvature of the universe. The stunning result, finally announced in 2018 after years of painstaking analysis, sent ripples through the scientific community. The universe, according to Planck's exquisite data, is remarkably flat. And not just roughly flat, but flat to an astonishing degree of precision, within a mere 0.4% margin of error. This profoundly flat geometry, as dictated by general relativity, strongly implies that our universe is infinite. It suggests a cosmos that stretches on forever, without end, a boundless expanse of stars and galaxies that never truly runs out. However, the story does not end there. Science has a fascinating twist, a realm known as cosmic topology. While a flat universe might seem to imply infinite space, topology suggests otherwise. What if this vast, flat sheet of spacetime isn't truly infinite, but simply wraps around on itself? Consider a three-dimensional version of the classic video game Asteroids. In that game, when your spaceship flies off one side of the screen, it instantly reappears on the opposite side, creating a seemingly endless playing field out of a finite one. In a topologically complex universe, the same principle could apply to space itself. You could travel in a straight line for billions of light years, only to find yourself back where you started, having circumnavigated the entire cosmos. Such a universe would be finite, yet still possess no center and no edge, just like the surface of a sphere is finite but has no boundary. It would be a finite cosmos that nonetheless feels infinite to its inhabitants, a truly mind-bending possibility that continues to fuel the quest for the ultimate shape of our reality, a cosmic balance beam held with impossible precision. That is the universe we inhabit, confirmed by the most precise measurements humanity has ever made. Data from the Planck satellite, scrutinizing the ancient echoes of the Big Bang, revealed that our universe is remarkably flat, not slightly curved, not dramatically warped, but flat to an astonishing margin of error, less than 1%. This profound flatness, however, isn't just a fascinating geometric quirk. It presents one of the deepest riddles in modern cosmology. Why is the universe so exquisitely balanced on the knife edge between being open and closed, between expanding forever and eventually collapsing back in on itself. It's a cosmic tightrope walk, and the universe has maintained its perfect equilibrium for 13.8 billion years. This cosmic conundrum is known as the flatness problem. In a universe governed by Einstein's general relativity, any slight deviation from perfect flatness in the early moments of existence should have been dramatically amplified over cosmic time. A universe born with even a tiny bit more energy density would have quickly curved in on itself, collapsing long ago. One with slightly less would have expanded so rapidly that no structures, no galaxies, no stars, no planets could ever have formed. The fact that we exist in a universe that is demonstrably flat, teeming with complex structures, demands a powerful explanation. It's as if a pencil was balanced perfectly on its tip for billions of years without ever falling over. The universe held another equally perplexing secret, dubbed the horizon problem. When we gaze at the cosmic microwave background, that glowing wall of light from the universe's infancy, we see an astonishing uniformity. Regions of the universe that were, by all accounts, far too distant from each other to have ever exchanged information or heat are precisely the same temperature, differing by only a few millionths of a degree. How could the universe on one side of the sky know to be the same temperature as the universe on the opposite side if light had not had enough time to travel between them since the Big Bang? It was a cosmic paradox that defied conventional understanding of cause and effect. Then, in 1980, a brilliant, audacious idea emerged from the mind of American physicist Alan Guth at the Massachusetts Institute of Technology, or MIT. He was struggling with an unrelated problem when a solution to these cosmic puzzles suddenly presented itself: cosmic inflation. It was not just a theory of rapid expansion. It was a radical proposal that the universe underwent an almost unbelievably violent exponential growth spurt in the first minuscule fraction of a second after its birth. Imagine a region of space smaller than an atom, a quantum realm, being stretched by an unimaginable force to a size larger than our entire observable universe. This was inflation. The mechanism behind the sudden cosmic growth spurt is theorized to be a hypothetical energy field, which physicists aptly named the inflaton field. In the fleeting moments between 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang, a duration so brief it is almost beyond human comprehension, this inflaton field dominated the universe. It drove space-time to expand at a rate so staggering that distances multiplied by a factor of at least a trillion. To put that into perspective, if your entire body inflated by that factor, it would become larger than our entire observable universe. This explosive growth wasn't just fast, it was exponential, doubling in size over and over again in fractions of a second. This mind-bending expansion elegantly solved the flatness problem. Consider a tiny, crumpled balloon. Its surface might be wrinkled and highly curved, but if you inflate that balloon to an enormous, unimaginable size, a small patch of its surface will appear perfectly flat to an ant living on it. Any initial curvature, no matter how extreme, would be stretched out and smoothed away by inflation to such an extent that the universe would naturally appear flat to us, its inhabitants, billions of years later. The universe didn't start perfectly balanced. It was forced into balance by this period of cataclysmic growth. Furthermore, inflation resolved the horizon problem with equal brilliance. It proposed that all the regions of the observable universe that appear uniform today were, in fact, once in very close contact, nestled together in a tiny, causally connected patch before inflation began. They had plenty of time to exchange heat and information, reaching a state of thermal equilibrium. Then, inflation took this small, uniform pocket of spacetime and stretched it to astronomical proportions, making those formerly connected regions appear widely separated and out of contact to us today. The universe's initial homogeneity was not a coincidence. It was a direct consequence of its inflationary past. But the story of inflation doesn't end there, for it leads to a consequence even more profound, a concept that stretches the very limits of our imagination, the theory of eternal inflation, primarily developed by the brilliant Soviet-American physicist Andrei Linde. If the infloton field is responsible for this exponential expansion, what if it doesn't decay everywhere simultaneously? What if, in vast regions of the cosmos, the inflaton field continues to drive expansion, constantly spawning new universes? This hypothesis suggests that our universe, vast as it is, might be just one bubble nucleated from an eternally expanding, chaotic multiverse. Within this grander cosmic tapestry, quantum fluctuations, the inherent jitteriness of reality at its most fundamental level, could constantly give rise to new inflationary bubbles, each peeling off and expanding into its own distinct universe. These new universes could potentially have different physical laws, different constants, and perhaps even different dimensions. The question, what is beyond our universe, transforms from a philosophical inquiry into a scientifically plausible scenario of an infinite cosmic foam of other worlds, a perpetually boiling cauldron of creation where new realities are born without end, extending beyond any edge we could ever conceive. What if everything we perceive, every star, every galaxy, every particle, is not truly three-dimensional, but merely a projection? What if the universe itself is an elaborate illusion, a cosmic hologram etched onto a distant, two-dimensional surface? This idea, once relegated to the realm of science fiction, has now emerged from the cutting edge of physics, forcing us to redefine the very concept of reality and the universe's ultimate edge. Our journey through the cosmos has shown us horizons of perception and limits imposed by time, but this theory offers a boundary unlike any we have encountered before. For decades, physicists have wrestled with one of the most profound intellectual challenges, reconciling Albert Einstein's sweeping theory of general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, the strange and unpredictable rules governing the microscopic world of atoms and particles. These two pillars of modern physics, each spectacularly successful in its own domain, fundamentally clash when applied to extreme environments, especially at the heart of black holes. It was precisely this conflict that gave birth to the astonishing idea that our universe might be a hologram. The catalyst for this radical concept came from the enigmatic depths of black holes. In the 1970s, the renowned British physicist Stephen Hawking highlighted what became known as the black hole information paradox. According to quantum mechanics, information, the unique properties of every particle, can never be truly destroyed. Yet, if something falls into a black hole, it seems to vanish forever, taking all its information with it. Where does that information go? Does it simply cease to exist, violating a fundamental tenet of physics, or is there a cosmic memory bank preserving it? This was a puzzle that kept theoretical physicists awake at night, threatening to unravel the very fabric of our understanding. A crucial breakthrough came from an unexpected direction, from the work of Israeli physicist Jacob Bekenstein. In his groundbreaking research, Bekenstein theorized that black holes possess entropy, a measure of disorder, or, more accurately, the amount of information they contain. But here's the truly shocking part. He proposed that this entropy, this maximum amount of information that a black hole could hold, was not proportional to its volume, as one might instinctively assume, but to the area of its event horizon, the two-dimensional surface beyond which nothing, not even light, can escape. This was profoundly counterintuitive. In our everyday three-dimensional world, the storage capacity of a hard drive, or the amount of liquid a container can hold, scales with its volume. But Bekenstein was suggesting that for the most extreme objects in the universe, the information content was somehow linked to a two-dimensional boundary. Think of a sphere. Its volume increases far more rapidly than its surface area as it gets larger. Yet, for a black hole, the information was apparently encoded on its skin, not throughout its interior. This discovery hinted at a deeper, hidden connection between information, gravity, and the geometry of space. Building on Bekenstein's startling insight, physicists Gerard Hooft in the Netherlands and Leonard Susskind in the United States independently developed and championed this idea, eventually formulating what we now call the holographic principle. At its core, the principle posits that all the information needed to describe a three-dimensional volume of space can be entirely encoded on a two-dimensional surface enclosing that volume. Just as a conventional three-dimensional hologram, which gives the illusion of depth, is projected from a two-dimensional film, the holographic principle suggests that our entire three-dimensional universe, with all its stars, planets, and living beings, might be a projection from a much simpler two-dimensional reality existing at its boundary, or cosmic horizon. This completely reframes our quest for the edge of the universe. It is not a place you could ever travel to, not a distant barrier in space or time that we might one day reach with faster-than-light ships. Instead, the edge becomes the very substrate from which our perceived reality emerges. It implies that space and time, the very dimensions we inhabit and measure, might not be fundamental properties of the universe at all. Instead, they could be emergent phenomena, born out of a more basic, information-based reality that resides on a distant two-dimensional surface. This highly theoretical, yet profoundly elegant, concept offers tantalizing potential solutions to some of the most stubborn problems in quantum gravity. If our universe is a hologram, it provides a mathematical framework for unifying gravity with quantum mechanics, potentially resolving the information paradox by suggesting that information is not lost but simply re-encoded on the black hole's event horizon. It transforms the vast, seemingly endless expanse of the cosmos into something akin to a grand cosmic display, where the true data of existence resides on a flat, information-rich canvas, projected into the dynamic, volumetric world we experience every moment. What lies beyond the edge, then, may not be more space, but the very source code of our reality, written on the ultimate cosmic horizon. For millennia, across continents and through countless civilizations, one fundamental question has echoed through the human mind, a question as old as curiosity itself: what lies beyond? This profound inquiry, etched into our very psychology, has driven us to chart every ocean, scale every mountain, and ultimately to cast our gaze into the boundless cosmic ocean. We have journeyed through the annals of human endeavor, from the chilling words, "Here be dragons," emblazoned on ancient maps, hinting at the terrors beyond a known world, to the astonishing realization of a universe teeming with billions of galaxies. Our quest began with the most intimate of scales, mapping the very Earth beneath our feet. We moved from a flat world with a definitive edge to a spherical one, where the boundary transformed from a physical precipice to the psychological challenge of circumnavigation, a feat embodied by explorers like Ferdinand Magellan. Then, the revolution truly began. The quiet, persistent work of a forgotten genius, Henrietta Swan Leavitt, provided the cosmic key. Her meticulous observations of Cepheid variable stars, initially dismissed as mere women's work, became the crucial standard candle, allowing Edwin Hubble to shatter our perception of a solitary galactic island and reveal an ocean of island universes, galaxies like Andromeda, located millions of light-years away, forever expanding our cosmic address. Yet, even with this grand unveiling, the universe presented a new, even more profound boundary, the glowing wall of the cosmic microwave background. This is not a barrier in space that we could ever reach, but a temporal horizon, a luminous veil at the universe's earliest moments. We learned it is the surface of last scattering, the universe at a mere 380,000 years old, before which it was an opaque, superheated plasma, a cosmic fog that no telescope, no matter how powerful, can ever pierce. It is a fundamental limit to our vision, imposed by the very laws of physics, a silent reminder that some beginnings remain eternally hidden from direct sight. We then confronted the very geometry of existence, pondering if the fabric of reality itself is a sphere, a saddle, or an infinite sheet. The astonishing precision of the European Space Agency's Planck satellite, mapping the cosmic microwave background with unprecedented accuracy, revealed our universe to be remarkably flat. This flatness, to within a mere 0.4% margin of error, strongly implies an infinite cosmos, a boundless expanse stretching forever in every direction. However, the fascinating twist of cosmic topology reminds us that even a flat universe could be finite, a three-dimensional version of a video game that wraps around on itself, offering a journey without end, yet still confined to a limited volume. These profound revelations led us to the mind-bending theory of cosmic inflation, a concept that elegantly explains why our universe is so perfectly flat and uniformly smooth. It posits that in the first minuscule fraction of a second after its birth, a hypothetical inflaton field caused spacetime to expand at an exponential rate, stretching a quantum-sized region into something vastly larger than our entire observable cosmos. This radical idea then spawned the even more audacious theory of eternal inflation, suggesting that our universe is but one bubble, nucleated from an eternally expanding chaotic multiverse, an infinite cosmic foam, where new realities are perpetually born, each with potentially different physical laws, transforming the very question of what lies beyond our universe into a scientifically plausible scenario. Most recently, we confronted the truly radical possibility that our universe, with all its stars and galaxies, might be an elaborate illusion, a cosmic hologram. This speculative conjecture, born from the struggle to reconcile general relativity and quantum mechanics, particularly the black hole information paradox highlighted by Stephen Hawking, suggests that all the information describing our three-dimensional reality might be encoded on a two-dimensional surface at its boundary. It redefines the edge of the universe, not as a place you could travel to, but as the very substrate from which our reality emerges, implying that space and time themselves might not be fundamental, but emergent properties of a more basic, information-based reality, written on the cosmic horizon. So, as we bring this cosmic journey full circle, we must ask, what is the ultimate answer to the question, is the universe infinite? Perhaps the precise answer is less important than the nature of the question itself. Every edge we have encountered throughout history, the edge of the Earth, the edge of the galaxy, the edge of visibility, even the hypothetical edge of a holographic reality, has consistently revealed itself not as a true end, but as a horizon. A horizon is a limit of our current understanding, a boundary imposed by our technology, our perception, or the laws of physics as we currently comprehend them. It is a place where the known meets the unknown, a perpetual invitation to push further. Instead of a single, definitive conclusion, the universe offers us a spectrum of astonishing possibilities. We grapple with the leading narratives, a truly infinite, flat space that stretches on forever, a finite, yet unbounded, toroidal universe that wraps around on itself, or a single bubble in an eternal, frothing multiverse, where countless other realities constantly emerge. These are not just abstract ideas, they are competing narratives that ignite the scientific imagination, driving research, observation, and theoretical breakthroughs, propelling our understanding ever onward. In the spirit of the great cosmic storyteller Carl Sagan, the universe's most profound secret may not reside at some distant, ultimate edge. Its greatest wonder lies in its astonishing capacity to produce minds like our own, minds capable of asking these questions in the first place. It is this innate, insatiable human impulse to map, to explore, to comprehend, that forever pushes the horizon of our knowledge outward, ensuring that the cosmos remains a realm of perpetually unfolding stories, a grand narrative that continues to write itself with every new discovery.